Just a quick correction. This is not going to be a review paper. It's actually a research project that we just finished. But anyhow, yeah, it's my pleasure to be here online today. I'm an assistant professor from the Department of Architecture at the University of Hong Kong. So I am an architect and computational designer. My research concentrates on the applications of generative computing, game theory, autonomous systems, and robotics in thinking about how to use them designing the built environment. So I will start my part by introducing the sort of the general motivation of our research. Nowadays, I think this project was basically motivated by the recent development of generative AI technologies, especially large language models and text-to-image generation models, because we see all the time, more and more images are generated online using natural language, and we see a lot of platforms like Midjourney, DALL-E have becoming communities, and where we can see people sharing their concepts and ideas through images. But one thing I noticed very interesting and critical is many of these users who generate images, they are not necessarily professional designers, right? Or who receive specific training for graphics. That's why I think my team's hypothesis for this project is in the near future, design process can become more and more a multiplayer game in which professional designers will need to co-steer the search of solutions, but with non-professionals. And so that's, I think, will keep the design process more and more open and more democratic. But also it can raise new emerging issues. Right? One issue is that many design solutions generated through image representations can be elusive. They look realistic or authentic in a way, but when you materialize and think more concretely how to realize that design, it may not work. Right? So therefore, I think the knowledge and the professional knowledge that and the digital or design models that work with the professionals need to establish a connection with the image generating process. And another issue is images can be generated by multiple people and who sometimes share similar expectations, but sometimes they may not, right? They could share expectations that are mutually exclusive to each other. And because by nature, none of us as a designer, as the users who engage in the design, we are not obliged to collaborate, right? So there are mutually exclusive ideas. So that's why we need probably potentially a computing agent that can better help us, right, understand the visual features of images of the representational ideas, but also at the same time can sort of maintain the objectives that we want to achieve in the professional understanding of any design outcomes. Right? So these two issues, but also there are the objectives that we want to achieve in this paper. So the method that we are starting with is something already mentioned a couple of times. So the first step is we established our own game model. And by the way, we are currently using the chair, right? Like where we sit, the chair as a very minimum sort of like a spatial object to design and to experiment with our method. And so to train this game model, we download and prepared CAD chair models from a database called ShapeNight. And so there are around like 864 in total chair models. And so we use these data sets to feed into our neural networks to train both the generator and the discriminator. So as the previous presenters mentioned that the generator and the discriminator, they will compete with each other in order to find out generate more realistic solutions, but also at the same time can distinguish the differences between a generated model and then a real designed model. So we tried a couple of different architecture of the neural networks, and then finally find one that can sort of give us the satisfactory results. I think the game model previously, there were a lot of like discussions about how we can reduce, for example, the noises and how to make them more realistic. But to us, I think the beauty of game model is it providing a generator, but also at the same time providing a discriminator. And so in our research, I think the discriminator is much more highly evaluated in our case. Because finally, what we want to achieve is to establish the connection between generative AI and the digital design space that normally a professional designer will work with. But at this point, we can see the generating process is still just using, for example, a stochastic series of numbers to create all these chair forms. And then the discriminator will recognize, okay, whether a chair model is realistic, right, based on the database we have or not. So I think that kind of like evaluation is still quite superficial in a way. We need a more in-depth understanding of the relationship of how to look at an image and the 3D model. So the second step we took was to implement another more kind of like improved version of GAN. It's conditional generative adversarial network. So sometimes we call that a CGAN model. So the conditional GAN model actually can was originally invented to establish the connection between two images, right? So we know the method published a couple of years ago as translating one image to another different style. I think in our case, what we need to achieve is just a little different in terms of its dimension. So in our case, it's actually through the translation is from 2D to 3D. So, and then we want to establish it's a more synthesized data set combining both 2D images and 3D models. So we just run the script quickly to take screenshots of each of these digital CAD models that we download. And then in total, like basically every 10 degrees, we take one screenshot of the model and compiled into a data sets of, so every single chair, it has 36 images corresponding to that. And then both the images and the models are fed into the conditional GAN networks. And then for the generator, we implemented a UNet structure. So it was proposed to be very well in terms of recognizing data-to-data similarity, especially when are short of data. And then the goal of the generator is still try to generate chair models and on the condition of an image, so that the discriminator cannot tell that they are actually describing the same object or not. And then the discriminator will just keep improving itself to know that a 3D model and then a 2D image, how well they match each other. So that's the goal of the generator, and this is actually the network structures, and that's the discriminator network structures. So again, right through, but this time, a very long time training process. We run this for 200,000 of steps in order to finally realize something that is recognizable, because to know the performance of GAN, it's actually quite straightforward, because we can just as a human, right? You just look at the results, and if it's getting closer to something real, that means it's performing well. So as you see in this case, the generating process keep reading this image. This image can be any angle from a chair model, right? It could be stochastically picked angle, but then the generator has to make sure it create a 3D model correspondingly. And the way we evaluate the performance of both the generator and the discriminator is if one of them performs well, we assume the other one is also good enough, right? At least it's not a bad one. So in this case, we can assume that the discriminator in the game model, in the secant model, is also performing well. But also we noticed that in the training process, because every single 3D model has so many images compiled with that together, so it's actually quite a large data set, and sometimes can take quite a long time to train. And also, but also we have to use as many angles as possible, because as you see in this diagram, the more angles of the screenshots we use, actually the better performance, and which is naturally makes sense, right? Because we see more features from different angles in the future when we see a new 3D model and a new image, right? We know better how they likely match each other or not. So finally, we used not all the 36 angles. We actually most of the front ones, because some of the ones looking at the back of the chair, at this point we found it's already kind of like not necessary to include in, but it's definitely kind of improving the performance further. But now you can see this is actually to just input the image one by one, and you will see the 3D model generated by the generator. It's actually pretty much matching the features in general, right? In general sense, with the image. And if we switch to another image that's describing another chair, the model can recognize that and can generating another model, a 3D model. And you can immediately see there are distinguished features, right, emerged from the 3D space. Right, so that's kind of like a proof of the performance of the new generator, right, the second generator and the discriminator. And then we started our third method of thinking about how to link the evaluation process with the digital design process. And so in this part, we further implemented the secant model to becoming an evolutionary secant model, which we will explain very shortly, right? So basically the idea is we want to create a more universally applicable design model, parametric model, that every single time the design solutions can only be produced by the combinations of design parameters. And then right now we're just using evolutionary solvers to help us to sort of doing this trial and error process to find the solutions that can best be evaluated by the discriminator that matching the images. But also, first of all, we created our own images of chairs by using text prompts. And this is actually generating using one of today's very popular platform, Midjourney. And there are functions like variations and upscales that we finally can produce some images, which we know they are generated images. So there is not necessarily an object correspondingly representing that, right? So, and then we feed the image into the computing process. And so basically the discriminator that we just trained, we will read this image together by reading another model that generated in the digital space. And then using evolution solvers, we will just do the trial and error process of the combination of the design parameters until we find the one that best match the 3D model produced from the digital design space that best match the features described in the 2D images. But at this point, you will probably also realize we definitely need some parametric model that is generalized enough, that has the capacity to give us the freedom of generating variations of design solutions. So we implemented this parametric sort of universally chair design model using graph theory-based IO system algorithms. And basically, we also manually tried the combinations of the design parameters using exemplars that are designed by famous architects or designers of these different chairs, right? So we played around with the parametric model to make sure, okay, most of the time, the degree of freedom, at least we can meet the requirement. So once this part is implemented, we can finally run our experiment. And but before explaining that, I want to mention that again, right? So we have the generator and the discriminator, but another reason why we want to use the discriminator by intentionally abandon the generator from the secant model was because, as you see in this image, right? The top line models generated from the SIGINT generator was most of them are quite noisy, right? And we cannot guarantee that they follow, let's say, the topological connections, and they follow certain criteria that we want to understand their performance. So that's why, to overcome the illusions of generating process, I think we intentionally want to use actually more knowledge-based, graph-based topological connection, meaningful parametric models to generate a design. But then the discriminator that we trained can help us to evaluate the design, how well it is matching, right, the image describing the expectations and such. But also this evaluation can combine with other performative evaluation criteria as well. If we want to understand the structural performance, the graph theories based model can definitely be helpful to include that as well. But at this point, we just include just another very simple criteria to reduce the amount, the volume of the chair as a whole, right, as another secondary criteria to run this process. Right, so then finally, we implement the evolution solver, the discriminator that just trained from the SIGINT model together as a holistic computing process. And then we use the plugin of Grasshopper called Velocy to help us. Basically, we don't have to manually program the evolutionary algorithm. We can just use the current library to support the trial and error process. On the left side of this page, you will see it's actually a single objective solving process. And sooner or later, you will see it's actually converging into one solution. And then the one in the middle of this page is actually using multiple objectives, so that even though like in the later stage of this evolutionary computing process, there are still trial and error, try to find a new balance between the two criteria. And you can immediately see the differences between the solutions that we find the best matching, right, in the single objective, and the best matching the two multiple objective version of the computing process. But on the third column, it was actually using the SIGINT model discriminator. So in the third column, design solution computing process, the image started to play a crucial role in deciding the solutions. So every single time, right, we decide which image we want to input into the system. So it's also deciding by considering how well the 3D model match with this 2D, described features. But actually, if we want to really think about the 2D and 3D matching, right, it's a visual cognitive knowledge that almost every single designer, human designer, possess, right? But to translate this knowledge to machines, it just took us quite a while and to figure out how to do this. And then finally, if we just look at just brute forcefully look at the results, I would say, the evolutionary SIGINT computing process is somehow, manipulated to know the features of the 2D images in three-dimensional way, right? Because when we look by our naked eyes, we can see the design is actually changing by using the different images as the guidance. But also we can also pick certain features and know it's actually not like a random decision. But at this point, we also want to go a little bit further, and also responding to the title that our paper, what the reason why we call the paper non-cooperative computing, it's because so far we have a game model, we have a SIGINT model, and the game model representing a knowledge that is coming from a database that is collecting from existing designs, which we could say this is knowledge representing the professional designers kind of examples and work. And then the SIGINT model, which is actually producing an evaluator or discriminator, and that is representing the connection between 2D images that are purely generated or using existing ones, right? And with a newly generated 3D model. These two models, I was wondering, like the knowledge, they are actually representing very different things. And they might also be mutually exclusive as well. And also at the same time, as I mentioned in the very beginning, what if we have multiple people that keep generating multiple images, but then all these images become the guidelines together, right, to generate design solutions. So that's why we sort of further improved our model to include both the gain discriminator and the secant discriminator together in the evolutionary computing process. And then this time you can see the database is actually becoming a criteria, because we have to always check whether the solutions is similar to something in the database. And also at the same time, we can create new constraints like reducing the volume of certain fabrication constraints. But then at the same time, we can keep increasing the images to make sure that it's not just using one image to drive the process. It could be multiple people, right, all providing their design intentions in this system. So in the end, it's still actually working. And after through iterations of computing, we can actually see in the end, it's sort of like a going around to also pick certain features from the previous best solutions. And then we can see those features all happening, right, again, in the finally sort of like a more synthesized and more holistic evolutionary computing process. Right, so that's so far what we have achieved. And I think to just summarize this paper, in the future, we can see a lot of potentials. One thing is, I think the meaning of doing this is to try to see how the design process become more and more open and become more and more democratic in a way. And and also, but at the same time, we realize the evolutionary solvers that we are using right now are too limited, right? Because they are just doing these very basic trial and error processes. But if we intentionally want to do the design parameters combinations, we need more intelligent agents. So for example, reinforcement learning can be a potential more promising method that we should explore. But also, we were also thinking about how to expand the research into large-scale build environments. And so far, we already tried something, let's say design a house, right? Design a villa. We sort of like also thinking about the process, and actually many parts can implement it in the same manner. And but also the database can become more complicated, right? Because once it's expanding from furniture to building, the spatial forms, how we construct the database become more and more complex. But also we can still rely on many of the time that using graph theory space syntax to help us to sort of finding the universally applicable design parametric models. And then no matter how many parameters there are, I think with the help such as more intelligent agents like reinforcement learning, we know they can play Go games, they can play much difficult games. I think that they can play design games as well. So I think that's kind of like the future perspective that where we can see this project will go to, right? So thank you for your attention, right? So that's my part.